差不多就是好了，还是把它差不多就这样，你就可以把它放进去。没问题，有吧？本来就是需要想象的。没事，还有。
Okay, so good afternoon everyone. So I think we can start now. Firstly, I would like to introduce myself and the juries later. After they introduce yourself for your team, from the captain. I'm from this campus, National Taiwan Normal University. I'm Yan Wenlan. Okay, so next, Professor Liu, you can introduce yourself.
Good afternoon everyone. I'm Liu Daiyin from National Indong University, Indong 大学。
杨佳慧 from Fengjia University.
Hi, my name is Xu Minchen. I'm also from National Taiwan Normal University.
Hello everyone, I'm Yi from Fengjia. Thank you.
Okay, so we start from the reporter.
Hello everyone, we are Team Epsilon from Kaohsiung Senior High School, and I'm the captain Xu Yisheng, Wang Yingxuan, Chou Yudeng, Xie Haoren, and Li Haoze. Thank you.
Okay, so reviewers.
Hi, judges and competitors. We are no-nighters. I'm Captain Darren Z with Ethan Hu, Billy Lim, Ethan Cho, and Kenneth Bo.
Okay, finally, opponent.
Hi everyone, we're Team Wagwa, and we are from Qingxin High School. And I'm Captain Huang Hongjing, Xu Changxin, Yuan Yiting, Huang Yuhong, Xie Shangzi.
Okay, thank you. So now, we start the competition. So firstly, the opponent please challenge the reporter for the province.
Okay, we would like to challenge problem number 2, oscillating speed.
Okay, so you will have 1 minute to make a decision.
Okay, and we will accept the challenge.
Okay, so the reporter, so you have the 5 minutes to prepare your presentation. And in the meanwhile, so please write down your name on the paper. reporter. Yeah, if you are ready, you can start.
Honorable juries and fellow competitors, my name is Ethan Xu from Team Epsilon. And for today's topic, I would like to talk about problem number 2, oscillating sphere. So here's the problem statement. It states that a light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis, thereby twisting the wire, and then released, it will start to oscillate. Investigate how the presence of the magnetic field affects the motion. For our preliminary observations, without the magnetic field, the sphere oscillates back and forth. So in the presence of the magnetic field, when we apply a thousand Gauss uniform magnetic field on the spheres, the oscillates will thin down quickly. And here is a graph about the angular velocity to time. That we can know that when we add 1,000 Gauss, comparison between 1,000 Gauss and 0 Gauss, we can see that the oscillations will decrease barely in 1,000 Gauss. And here's the experimental setup and the analyze method. For the setup for this problem, we create two electromagnets, and we provide a ball wrapped with the aluminum paper to make sure that it is conductive. And then both of the electromagnets will make sure the diameters is larger than the ball to create a uniform magnetic field. And we can see it as our simulations. The electron curl in the Helmholtz conditions to generate the uniform magnetic field in the middle part to make so we place the ball in the middle part to make sure it is uniform. And we use tracker for analyze the trajectory of the theta, and we use the Python for the data analysis. And for categorizing it as oscillators without the magnetic field, we can first return the equation of motion as a torsional pendulum. So we can resolve the equation of motion into 3 parts: angular accelerations, damping terms, and torsion constants. So in our cases, we first know that it is under damping. So we can write the theta trajectory under damping terms, and then we will going to find the omega 0, and our gamma, which is our actually damping terms in these cases. And here's the paper review. In this paper, it introduced about the 2 different cases. For case 1, that the magnetic field will acting parallel to the torsional axis, and then as case 2, it will vertical to the rotation axis. So to consider a uniform magnetic field along the z-axis with the rotation axis, we can first create a geometry about the ball in our correlations. So we can expand the geometry about the balls written as an equation, and then the velocities can written as an equation as follows. And to find the electron motion in the electromagnetic field, we will combine the generalized Lorentz force and the charge conservations. So we combine both equations together to get the equation here. And to use the equations, we can calculate the tangential charge density, which is rho T. By calculating the tangential charge density, it can lead to the tangential electric field. So getting the electric field, we will solve the electric field over the V cross B. As a total electric field, we can apply to lead our electric field into a Lorentz force equation, and then we get the surface current density equals to 0, which means there is no magnetic force and magnetic torque works on the balls. So it seems that the damping won't have the magnetic damping term. So here's a chart about the charge distributions on the rotation spherical shell in a uniform magnetic field along the z-axis. And here's case 2, that we also can build a geometry as a spherical correlation, and the rotation axis will define it as the x-axis that we can show as a picture. And we consider a uniform magnetic field along the z-axis, which is vertically to our rotation axis. And the velocity is then over the omega times r. We can expand our equation here. And we can also solve the tangential charge density and lead to tangential electric field. And by solving the electric field, we will get the electric field equation here. And as a result, we can find the magnetic force equals to 0, which means there's no the center of the mass won't move along in our uniform magnetic field. But the magnetic torque doesn't equal to 0. It is proportional to the negative accelerations, negative to our angular velocity. Which means it is acting like our damping motions. So in our derivations about the equation of motion in this system, from the Newton's second law in the rotation terms, that we can first write the net torque, and then we can use the derivation in our further derivations to find the magnetic torque. And we plug the torque together to rewrite our equation of motion that we plug the magnetic torque inside this equation. So it can be derivation, the equation of motion as still as an underdamping. So we can write a trajectory, and after resolving the beta here, we can add it in our damping terms. And for the data analysis with the Python, that we track the 2 points on the bottom of the sphere to find and plug it into Python for the calculated about the theta and the omega. About how to change the different positions into the theta trajectory, I will introduce here that here's the trajectory that we track on the 2 different points, and then we can change it into the slope by using the 1 point minus another point. We can find the slope between the 2 points, and then we can calculate the angular to time, and then we can change our angular into theta. So we will write the graph about the theta to time. And here's the first experiment that we will add the magnetic field strength. We will define it as B. In our model, the magnetic damping is proportional to B squared. And here's the uniform magnetic field that we're going to provide it in the aluminum sphere. And after our derivation, we know that it will only act on that when the magnetic field is vertically to our rotation axis. And so we write the equation of motion here, and we are going to using the fitting to find the gamma, which is the damping terms. And here's the result. Here's a video about the 0 Gauss, 100 Gauss, and 200 Gauss and 300 Gauss that we will do in our experiment. We can see that 300 Gauss can barely stop faster than the situation that we didn't add any magnetic field in it. And so here's the result to fitting about the gamma 0, which is that under the situations that we didn't add any Gauss. And here's the result for that we're applying 100 Gauss, that the fitting result, which is gamma, we can written here. And here's the result for 200 Gauss. And as a result for 300 Gauss, we can see that it decreased very fast, which means there is very similar to the underdamping, but is still the damping that we assume. And here's a comparison between the different parameters. So we can find the curve that will increase when we add more magnetic field in uniform magnetic field on the sphere. And here's a second result, that to find a magnetic field direction. In our experiment, we can't change the rotation axis versus the magnetic field direction. So to investigate the similar effect, we modify our experimental setup that we only use a conductive ring for the experiment. And so here's the experimental setup that we have the 0 degrees, 30 degrees, 60 degrees, and 19 degrees. And here's the result for 0 degrees, which is that the conductive ring is parallel to the magnetic field. And here's the result. We can see there's not easily to be observed the effect of all the magnetic field. And here's the result for 30 degrees, that there have some little effects on the magnetic field, but it is not very to be observed. And here's the result for 60 degrees, that the effect of the magnetic damping terms has worked on the sphere. And as the result for 90 degrees, that we can see the damping is easily as the fold, that we wrap the fold bolts. And here's a comparison, that when the tilting angle about our conductive ring it has increased, that the damping terms will also increase. And here's the discussions about the conductive ring in our own theory derivations. To gain a qualitative understanding and better physics picture, we revisit the theory by consider our rotation conductive ring in the magnetic field. So since the ball, to find the direction works on the ball is very hard, that we can draw a physics picture that about the ring. So we can, as our paper review, we will know the direction of the current, and so we can use our right hand to find the force about the Lorentz force. And that we can write the equation here to calculate the average torque that will proportional to our negative angular acceleration. And as the acceleration without the magnetic field, the sphere oscillates back and forth, and in our presence of the magnetic field, the oscillations will damp down quickly. We can look at a video and also can look at our angular observation to the time. And as the paper review, we review a paper which studied the phenomenon. They studied two cases and shown that in case 2, there is a torque, that when the magnetic field is vertically to the rotation axis, we can write in the equation about the torque. And here in our model, with the paper duration, the theoretical modeling our oscillator as a damping harmonic oscillator in the form of a torrential pendulum. So we will add the magnetic damping terms into our equation of motion, and we can use fitting to find the gamma, which is that we will explain as a damping. And here's the experimental result. We experimentally explore how the damping is affected by the magnetic field strength and the tilting angles. After adding more magnetic field, that's the magnetic damping coefficient will increase. And when the tilting angle has also increased, the magnetic damping coefficient will also increase, since that we have known the direction about the eddy current. So about the discussions, we developed a simple physics picture to explain the phenomenon by considering a rotation conductive ring. And here's a side view about our current. And in the top view, we can use our right hand to find the force direction about the Lorentz force, and the two-side Lorentz force will apply the torque, which is proportional to a negative induced current. Negative induced current to make sure that it will dampen over the time. So as our result, we can see as adding more magnetic field, the damping terms will also increase. And then as a torque, we can find we will find the relationship between the magnetic flux. And changing the magnetic flux, we can find the induced current on the surface of the sphere. And I will say, here's all of my presentation. Thank you for your listening.
Okay, so opponent, please ask the question.
Okay, thank you for the reporter's report. And I would like to know that what is the material of your line you use?
The material of the line.
Line.
We use a thin wire to do the experiment.
Okay. In the experiment, you talk about the damping, and what kind of factor you think will affect the damping?
About the fact, like the parameters that will work on the damping.
What kind of things will affect? What damping?
There are two dampings in our equation of motion. The first is the damping that's caused by the connecting with the wire. Another is the provided by the magnetic force, and the magnetic torque works on the sphere.
Okay. How about the resistance of the air?
Yes, we consider the resistance of the air in a part of our original damping terms, which is we will write it as a gamma 0. Which is also known as beta 0 in our equation.
Okay. How about you think that if the ball is hollow, what will happen?
Yes, our ball is hollow in our experiment. Since we know that in our real world it's not provided an ideal conducting material, which means in every material there is an electric field will provided in the center of the material. So to acting like a sphere, ideal materials in our real world, we use a hollow sphere to ignore the effect of the electric field inside the materials.
Okay. Can you move back to page 18? Can you talk, explain this graph again?
Okay, I would like let we have the two points here, x1 to y1, x2 and y2, and we can find the slope between the two points. So far, so good. And then by changing the slope into the angle, we can find the trajectory about the.
Okay, time's up. Okay, 3 minutes for preparation of the opponent. Opponent, please take a blow.
Hello judges and competitors, this is Huang Yutong from Team 112. And today I will be opponent the problem number 2, oscillating speed. And for the public statement, a light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis and then released, it starts to oscillate. Investigate how presence of a magnetic field affects the motion. And our main focus today will be on the strongness of magnetic field and also the direction of the magnetic field, like whether it is parallel or vertical. And first, I will going to talk about the pros and the cons of reporter. For the pros, they made the comparison between the original and the magnetic field that they added. So they changes different mechanical field and to find out its results. And the second is they introduces paper review and discuss multiple cases. And third, they created clear theory in discussion. That they use a lot of different formula to talk about their experiments, and which made that their experiment like more complete. But for the cons, I think they can combine multiple theory more clearly because like they talk about many different theories, but I think it's better for them to like talk about their the relations between each theory and also the relations between the experiments and also between the experiments. And also, I think they can make the sphere fixed to avoid swinging that might cause deviation. Because from the experimental video, you can observe that even though the sphere is twisting, but also we can observe that there is still some a little bit swing of the sphere. So I think maybe it will cause some deviation. So I think maybe we can have some ways to like decrease the deviation, and maybe it is something that we can improve in the future. And for the discussion, I think for the reporter they didn't talk much about the distribution of the particles. So I think it may affect the turning of the sphere. So I think maybe this is something we can discuss about in the following states. And also, we can have a discussion about the damping. For example, such as what I have already mentioned is what kind of damping they think. And also for the third one, I think we can talk about what if we cut down some parts of the sphere and how it will affect the phenomenon. Because just like what the reporter have mentioned in the short question, they say that the eddy current will only happen on the surface of the sphere. So they say that they use the hollow sphere. So I think if we cut down some parts that of the sphere, so maybe it will have some difference. Also for the fourth one, how does the energy changes through the oscillation? For the reporter, they didn't talk much about the energy of this experiment. So I think that is what we can discuss about in the following. And also later I will want to invite the reporter to come and have a discussion. Thank you. Okay, first, I would like to know that what kind of damping is emotion.
So as we know, there are three types of damping, which is over-damping, under-damping, and critical damping. And in our cases, we think that in our cases, I think we will think if it's under-damping, things that the bolts will that rotation in an extreme volume, and then it will twist and move back and forth.
How about if the resistance of the electric is too big, will it become critical?
Yes, I would agree with the opponent. Since in our experimental results, we think that when we add our magnetic field into a 300 gauss, that it will acting like a critical damping, but it still is an under damping that since is over the 0 point. And so I think if we provided more magnetic field on the spheres, I think we can use another trajectory, which is a critical damping trajectory to fit our result to find the gamma, which is the damping.
Thank you. Can we move that to the working? Can you show the distribution of the particles?
Okay. Please indicate about the that's in our cases for the parallel, when the magnetic field is parallel to our rotation axis, you can show here that the distribution about the red part will be the positive charge, and the upper parts will be the negative charge.
How about that if the magnetic field is over
Vertically to the rotation axis. This also have shown the result on our slide. I would like to draw it on the blackboard that we can see on my slide that the positive charge will be at here, and the negative charge will distribute at here.
why do you think that it will like this?
I think the since the tangential charge density changed and the tangential electric field will change, that makes the charge distribution.
Okay, for this condition, I agree with the reporter. I think that the distribution will also be like this. But for my explanation, I would like to use the right-hand rule to explain it. When we twist this sphere for this direction, the particle will have this direction, will come to this direction. So when we have a magnetic field that is from this direction,
Yes.
so so I think that it will become, if the magnetic field like this, I think it will become.
Oh, okay, I understand.
Yes. Can you?
I can
Okay.
agree with you.
So when we turn this for this direction, the direction of the particles will come this direction.
Yes.
But for the magnetic field, it will come this direction. So it will have the force that will come.
Okay.
So for the positive particles, that will go to the top. So it can. Can you explain how the particles move through this?
I think the force works on the surface to a charge on the sphere that will push, like the opponent says, push in a different direction as the picture that we shows. And then since that there has different positives and negative charge on the surface, it will induce the AC current on the surface. That makes the ball received, and we can add it as our damping.
Okay, so it means it's like this direction.
Yes. And we have also shown it as the direction of the AD current that we will move it. You can draw it as this side view. We can also draw it as it will vertically change vertically as the direction of the AD current.
Okay, thank you. And let's moving on to the next question.
Okay.
Since that you say that whether we use a hollow ball or not hollow ball, that it will not have differences between, according to the eddy current, it only happens on the surface.
May I re-answer my question again? Re-answer my your question.
Okay.
Since in our cases, we just discussed about the hollow sphere, but I think when we have the thickness about the sphere, that the workings on the particles working only on the surface, but the effect of the damping will change.
So okay, so that we both is so we both agree on the eddy current will only happen on the surface.
Yes,
Okay, so
we are on the same page now.
yes. So what if like this is a sphere and if we cut down these two parts of the sphere and
Yes.
what do you think what it will happen?
I think it's a very interesting action since we have discussed about in our experiment that the opponent mentioned it again, and I would like to discuss this question. That since we mentioned and after our discussion, we know that the direction we're moving that parallel to the rotation axis. So since you cut the two parts of the conducting surface, that it can't be a completely current on the force field. So in our experiment that we showed, one of the cases is that there we have mentioned about the 0 degrees, and as the 0, which is the parallel to the magnetic field. Yes, at the 0 degrees, we can see that there has a slow effect on the damping terms, but since that the direction of the eddy current is vertically, when we only take a part of the parallel side, the eddy current effect will reduce.
Okay, so that it means that if we like when we cut down these two sides, because of these charts, this picture we have thought that the direction of the particle will be like this direction. So do you think that it won't affect?
Could you talk about that to cut the both vertically,
Yes.
like the cases that we mentioned about 90 degrees?
Yes.
Yes, in these cases, we can take it out, take this part out to since it as it as the current that the direction we're moving at this. Yes. So far so good. And so in the side view, this is a bit about the discussion. And about the side view, we can cut a cross section about the curve. Then we can see as our picture. Then here, part of the current will move as this, and another will this way. And then we take the two, we connect the current together, then we build a vertical correlation axis. And we can use our right hand. And we know the direction about the Lorentz force will be the direction here, and the eddy current will go out. So the force about the Lorentz force will go this side, and another will go on the opposite side.
Okay.
So we provided the torque.
So you think that when we cut it vertical, the effect that will be almost the same as this picture?
Maybe the effect will kind of reduce, but I think the eddy current will affect on these cases.
Okay, so let's moving on to another question.
Okay.
Talk about the energy of the pole. And for energy, I think there are three energy in these cases. One is the kinetic energy, and another is the energy that is stored in the line. We can call it potential energy. That's repeat. And also for the magnetic energy that is given by the magnetic field, so that's called M. So now if we just don't consider this, for the K and P, the relation will be like this. Like this is K and then P.
Yes. So you think that the transfer between the kinetic energy and the potential energy on our Y.
Okay, so yes, so do you agree like this?
Yes, it will be transferred, but it will still have a damping effect that makes the energy decrease.
Okay. So now that if we talk about the whole energy of this experiment, so that it will be like almost the central if we consider the magnetic field, the energy, what do you think the charge will be?
Since in a theoretical result that we don't consider the damping of the wire, it will
Time's
be
up. Okay, close. Time's up. So opponent summarize the discussion.
Okay, for the discussion that we had, first we talk about the distribution of the particles, just like the picture already did. And I think we both agree that the distribution of the particle will like this picture, because that also tells us the direction of the particle, that how it moves. And also the second thing that we discussed about is that if we cut down two parts, will it affect? Because we both agree on when we cut it vertical, because we have said that the direction of the particles is like almost like this direction, so the effect will be bigger than if we cut down at this direction. And so for the third, we talk about the energy, even though we haven't finished it, but we all both agree that the energy.
Okay, time's up. So question from the reviewer.
Okay, so my first question is for both the owner and the reporter. So you tried the surface when the surface is conducting, but did you try a solid sphere if the whole thing is conducting?
Since I have answered the question to the opponent, if the solid sphere is being considered, that first of all, it will not mention about the light sphere in the power statement mentioned, and then we have to consider the electric field in the inside part about the materials. So I think to comparison between theoretical and our experiment, using the hollow sphere will be the better things to make the two theory.
Okay, so your model is for a hollow sphere. You
Yes.
have one for the solid sphere. So you don't have a theory for the solid sphere.
Since in our derivations we have considered about the thickness of the thickness of the
Okay, thank you.
bulb.
In our discussion, we both agree that the eddy current will only happen on the surface of the sphere. So I think that whether we use the sphere is solid or is hollow, I don't think we will have a theory.
Okay, but since our world is not ideal, do you believe that there may be some current that it goes like inside the sphere,
Yes,
which may affect the experiments?
maybe, but I think yes, partially agree with you. Yes, but it will mainly on the surface.
Okay. So, so what do you think is the effect of combining the strips? So let's say you have a strip here and a strip here, if the ball is here.
So you're talking about the cases about the tilting angle of the ring?
Yeah, if you have multiple rings combined in one strip.
I think it's a very interesting question, since we have mentioned about the direction of the AC current, it will be the vertical side. So if we have the multiple rings on the conductive ring on the sphere, it will, I think it will happen, the AC current will affect more, but in the cases that is clearly similar to the vertical axis.
Okay, and what do you think it will happen?
I will agree with the reporter, because just like what we have discussed, the direction of the particle is like the vertical direction. So that if we use the just like the direction that is vertical, so I think that it will be.
So for the reporter, in your experiment, did you consider the restoring force of the wire?
Yes, that we restore the energy in the wire. That can make it rotate. That is the reason that makes it rotate. Since if we don't store the potential energy inside the wire, the balls won't. The energy can transfer into the.
So you put it in a form
Okay,
of
time's up.
energy.
Preparation time, for reviewer, 2 minutes. Reviewer, please take photos.
Okay, so I'm from Known Riders. I'm the reviewer Darren Z, and we're talking about the oscillating sphere topic. And so the problem statement says, a light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis, thereby twisting the wire and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. So I believe that we should focus on the damping of the damping motion and the magnetic uniformity as well as the surface of the sphere. So the reporter in his phenomenon talked about the sphere oscillating in a magnetic field, which damps it down quickly. And then in his theory, he talked about how a parallel magnetic field has no effect, whereas he also pointed out the perpendicular. He created an electric field equation for a perpendicular case, and so he also talked about how the magnetic torque acts as a damping motion, and he mentioned angular acceleration, the damping, and torsion constant inside his theory. And so for the experiment, he did experiments on the trajectory of the ball and applying magnetic field, as well as using different types of conducting strips. And so pros are that he clearly demonstrated a phenomenon, and he has a rigorous theory. And then for cons, he did not really account for the release of an initial angle, and then his setup, his pendulum, there was a lot of pendulum motion, and it didn't account for tilt, and then so he didn't really explain damping that much, and then he did not experiment with a solid sphere. And so for the opponent, he pointed out the eddy currents and brought up damping that the reporter did not go into much in his presentation. So the pros is that he brought up damping, and he points out many missed points by the reporter, but but they didn't talk about the non-uniform magnetic field. And so during the discussion, they talked about the distribution of charge, and they explained the distribution of charge on the board, and how the motion of the induced current, the induced eddy current. And then, so the reporter specifies the motion of the charge, and we agreed that the motion that they pointed out during their discussion. And so they talked about eddy currents and like where the eddy currents are, and then so since they use a hollow sphere, the eddy currents, the reporter responds with the eddy currents are on the outside of the sphere, and we also agreed that the eddy currents are on the outside of the sphere when it is a hollow sphere. And so they also talked about the placements of the strip, and so the difference between the strip and a conducting surface. And so the reporter agrees with the opponent of the difference in the strip versus the surface, and we agree that the incline of the strip will affect the induced current. And so they also discussed about the damping effect, which is good because the reporter didn't talk much about it, and they talk about the direction of the magnetic field, as well as the energy of the ball at the end, but they did not finish their discussion. And so points missed is that the reporter didn't consider the solid ball case, which may affect the skin depth, and it may be a good thing that they can look into. And they didn't account for they didn't identify them for the magnetic field's generation and the opposing force as a main factor of the damping. And they also did not look into the non-uniform magnetic field, which may affect the damping of the ball while it is spinning. Thank you.
Okay, so concluding remarks from the reporter.
Okay, thanks both of the opponent and the reviewers for the point that about my presentation. And here are some concluding remarks that I would like to mention again. First, we simplified the model into a conductive ring to figure out the direction of the Lorentz force. Since that if we only consider a sphere, the direction of the Lorentz force will hard to be considered. And we used a uniform electric field to make sure our situation is under a theory condition. So I can also note that the non-magnetic field is an important parameter for these cases, but the non-magnetic field have different definitions, such that the diameter of the electric field is smaller than the diameter of the balls,
And we also use the different tilting angles to make sure our eddy current direction is correct. And we can also use the right-hand side to figure out the direction of the Lorentz force. And we also discussed about the charge distribution and the direction of the eddy current, and about the direction of the eddy current, we can also relate it to the direction of the Lorentz force that works on the boat, and then makes the boat recede. And also, I think the multiple ring situation is also interesting to be investigated, to do an experiment to prove it. And about the thickness of the sphere, I think it is hard to find the different thickness of the sphere in the same material. So in my opinion, I think there is more possible to use the theory derivation to find out the relationship between the thickness and the magnetic damping terms. And I would also like to talk about the charge distributions that the opponent talked about. Why is the charge distribution well on the surface? And so I think the thickness is also an interesting point to be discussed, since we know that the eddy current will only affect in our surface. But I think the thickness will also be an interesting point.
Okay, thanks up. Okay, so finally the question from the theorist. Okay.
Okay, so I have a question for all three teams. Please use the blackboard to write down all relevant energies in this experiment. And if possible, when angular variable is involved, just express it in terms of your angular variable. So all of the three cases, you will not be able to see other people's.
So do you mean the mechanical energy?
All the energies related in this experiment.
So we write like the case,
Just, you have to, in terms of when the angular variable is involved, just express it in terms of the angular variable. You can erase
To write down the energy works on the spheres or the
all the energy in this experiment.
Oh.
Okay.
Okay, so you're all done?
No.
Yeah. That's it.
Okay. So other question from jury? Okay, so Professor Liu.
So my question goes to reporter. So when you do this experiment, do you need to consider the magnetic field due to the Earth?
The reason why we only find the damping about the magnetic field acting damping, I think the magnetic field provided on the Earth will consider in the damping, original damping that we measured in the cases in the zero gauge should be considered inside.
Okay, so same question go to the other two.
Oh, can you repeat the question?
Yeah, do we need to worry about the magnetic field due to the Earth?
Oh,
I think compared to the magnetic field of the magnetic, I think the magnetic field of the Earth is like quite small, so I think maybe it's okay to ignore it, but it's better to also discuss the magnetic field of the Earth.
so obviously the magnetic field of the Earth affects it to a certain extent, but I don't think that it's big enough that we should consider it. So because you have two magnets right beside the ball, so that magnetic field is much stronger than the Earth's magnetic field.
Okay. So I think it's time to scoring. For reporter, 7, 8, 7, 8, 9. For opponent, 6, 5, 6, 7, 6. For reviewer, 6, 4, 6, 7, 7. Okay. So we take 15 minutes for break. Okay, now we start the second round. Opponent, please challenge the problem to the reporter.
You challenge the reporter to number 9, oscillating sphere.
Okay, so you have 1 minute to make a decision. Okay, so you have 5 minutes for the preparation. In the meanwhile, please write down your background. Okay, start.
Hello, I am the reporter from Team Waku Waku, and today I'm going to report problem number 9, oscillating screw. So this is the problem statement. When placed on its side on a ramp and released, a screw may experience a screw may experience growing oscillation as it travels down the nail. Investigate how the motion of the screw as well as the growth of these oscillations depend on reference parameters. So the main focus will be the oscillation will grow over time and the nail will be determined before release. So we think that the amplitude of the oscillation will increase, and also we can see the nail as a cone shape. So this is the outline I will be going to introduce about. First is the observation video, and then I'll talk about the theory and the experimental setup. And then I'll talk about the variables, the data analysis, conclusion, and also the discussion that we can do in our further experiments. So this is the observation video that we've made. So we can see that we used a wooden base as the seat, and we add the friction tape onto it because we want slower falling motion to observe the more oscillations of the nail. And also we can see that we put the nail in a determined angle that every time we drop the nail, we have the same angle because we want the total energy of the rotating motion to be the same. So we can see in the video that the screw rolls like a cone in an inclined plane, and while rolling, it's also constantly slipping. That means that it isn't just oscillating on the same surface. And the rolling motion is oscillatory, like that of a pendulum. We can see from the video, the nail is oscillating. And while the rolling stops or changes the direction, the screw exhibits a different rotation motion. So this is the theory. So in our observation, we can see that the nail has three motions in its movement. The first one is the falling motion. So we can note that according to the free fall equation, the acceleration in this picture is the g sine beta times the time is the acceleration times the time, which is the velocity that we can get in the moment. And for the second motion is the rolling on the axle 3, which is the rotation. So the omega here stands for the rotational direction, which means that it is rotating itself on the axle 3. And this is the third motion. It's the oscillation, which looks like a pendulum in our observation. That the amplitude of the oscillation increase when in our observation. So we can see that the final equation here is the total energy will equal to the kinetic energy plus the 2 rotational energy from the motions I have mentioned about, which is the rotation on axle 1 and also axle 3. And this is our experiment setup. As I mentioned before, this is a wooden base, and we use the friction tape because we want slower falling motion, and also we want to observe the more oscillations. So we want to decrease the falling speed. And also we printed different sizes of nails because we want to control that the material of the nails that we got is the same. And we have prepared 5 nails which the heads and the tails have different length and different radius. For nail A, we have 10 millimeters for the head and 20 millimeters for the tail. And for nail B, we have the same size of the same radius of the head but longer length of the tail. And for nail C, we got the heads and tails 1 to 3 for 10 millimeters and 13 millimeters. And for nail D, we got the same tail length, but we got the bigger radius of 15, and for nail E, we got 20 millimeters. And these are the variables in our experiment. The control variables is the friction on the slope, which we use the friction tape, and yeah, the slope is the same. And also the material of the nail that we printed is the same, and also the position of the release, including the height and also the angle, is controlled. And the independent variable is the length of the nails that we have printed and also the radius of the head. And the dependent variable that we want to observe is the position of the nail in different times. So we can watch the video that we used nail A and nail C, which the radius and the tail is 1 to 1 and 1 to 3 and 1 to 1. So this is the graph we got from the short nail, which the radius and the length is 1 to 2. So we can see that this is the oscillation of the nail, and this is the falling motion of the nail. So we can see that there is a straight line here, and we estimate that because we will estimate this as a deviation because maybe the friction will be different when the nail is falling. In some situations that there are some resistance that we didn't consider. However, in this one, it doesn't have the problem. So this is the graph from the long nail, which the oscillation and also the falling motion of the long nail, which the radius and the length is 1 to 3. So we can see that the periodic time of the oscillation is bigger when the nail's length is longer. And also, so as we can see in the graph, there is a difference in the period of oscillation. And comparing these two graphs, we can see that during the same time, there is a longer period for the 1 to 3 nail. And it can be predicted due to the pendulum period formula. So as we can see, that the longer the length of the pendulum, or I said the cone, the periodic time will increase. And also from the falling motion graphs, we can see that the decline of the longer nail is less steep, which means it has a slower downward velocity. And our claim is that because when we longer the length of the nail, the I here will increase. So the kinetic energy will become lower. So that's why it has a slower downward velocity, because the energies are mostly transferred to the oscillations. So in our conclusion, we can see that a nail drops and moves in 3 motions. The first one is the falling motion that I've mentioned before, according to the free-fall equation. And the second one is the rotate motion, that the nail rotates itself on the slope. And the third one is the oscillation motion, that the nail is oscillating on the slope. And so when we see our variables, we can see that when we have a longer nail, we can observe a longer period of oscillations for the third motion, and also a slower vertical velocity because most of the energy is transferred to the rotate motion and the oscillation motion, but not the falling motion. And these are the discussions, because in my experiment, we didn't change the angle of the steep, but we think that if we decrease the angle of the steep, we can decrease the kinetic energy. So yeah, that's a further experiment that we can do. And also we can consider the rotational friction, which the variables may be the mass of the nails or the shape of the nail. Because if we change the nail into a cone, the touching surface on the slope and the nail increases. So this might affect the oscillation. So this is what we want to observe further. And also the mass of the nail, if we increase the mass of the nail, we will increase the friction and may slower the rotation. And this is the end. Thank you.
Okay, so question from the opponent.
So first of all, in your initial experimental setup, could you explain why you left the gap in the friction gauge?
Which gap?
Could you go to your setup experiment? As you can see, there seems to be a gap in between the two friction gates. Could you explain why you left it in there? Or did you assume it to be negligible?
Yeah, we didn't. We want it to
Okay.
be.
How did you measure the friction coefficient of the tape? Did you calculate the friction coefficient of the tape?
No.
Okay.
Do you think the parameters you kept constant would make an impact on the motion of the screw? For example, the incline of the ramp, the incline of the friction coefficient between the ramp and the screw, and also
The heightness of the steep will influence the oscillation.
Okay, could you clarify what you mean by nail and screw? Because there is a clear difference between a nail and screw, because the screw has scales, and that affects the motion of the toggle. Could you explain why you 3D printed screws instead of 3D printed nails instead of screws?
For nails and screw, they have like a cone shape, and the touching surface is the same. We estimate it as the same because there are 2 points touching the surface, so we said it's the same.
Okay, so touching points. Did you attempt to calculate the inertia, moment of inertia for the rotation of the engine inertia?
Sorry?
Did you attempt to calculate the inertia for the moment of inertia for the kinetic energy?
No.
No, okay. And how did you make sure that
Guys up. Okay, preparation time for opponents.
Just do your presentation. Just do presentation. You have 2 minutes. You have to give me some not so much as to
Opponent attack below.
Okay, hi, I'm Ethan Hu from Team No Nighters, and I will be opposing the question oscillating screw. So as the reporter stated in the question, when placed on its side or at least a screw may experience growing oscillations, and we were tasked with figuring out the relative parameters of the growth of these oscillations, and tasked with modeling the motion of the screw. So first of all, observations. We believe that some good parts of the observation of the reporter was that they identified different types of motions in their energy formula, such as the different types of rotational kinetic energy. They identified that there was a growth in oscillations, and they had a clear phenomenon video. However, we thought that they didn't explain the motions fully. The ramp is too short to track more than a couple periods of the screw. They do not talk about the stopping of the screw under certain scenarios, and they don't consider different types of screws because they 3D printed all of them. And then they have an unclear reference to either a screw or nail, which are different things. In terms of theory, we think that the opponent did a clear job of explaining what variables they considered. They did consider inertia, but then they didn't really calculate what inertia would be. They had angular velocity in the calculations for kinetic energy. They didn't really calculate it though, and they mentioned different types of kinetic energy. Next slide. Oh, okay, yeah. For experiments, they accounted for multiple parameters, and they utilized different radius and heads. They also related the period to the length of the nail. For experiments, they didn't account for the separate normal forces on the screw, and then they tracked vectors from one section of the screw, which kind of doesn't reflect how there's two different vectors on the head and tail of the screw. And then the friction was not uniform in the experiment due to the gap in the tape. They also did not consider many of the parameters they kept constant, which have a significant effect on the growth of the oscillations. For data analysis, they showed the result graphs, which is a good thing. However, they did not attempt to quantify their equations, and they did not test the theory whatsoever. So in our discussion, I think it would be good to first talk about how we can model the moment of inertia for the different types of kinetic energy of the screw. We could also talk about where the screw pivots from, because the opponent did not mention where the screw would pivot or rotate from inside their theory. We could talk about how we could account for slip in the theory, because there is a rolling motion. However, the rolling motion can be clearly seen to not be completely translated to the translational velocity. And then we can talk about the presence of damping in the oscillations, because even though there is a growth in oscillations, we believe this is more of a driven damping oscillation, not just pure growing oscillations because of the presence of work done by friction. In terms of experiments, we could talk about how we could vary a couple of the parameters that we saw that were actually significant to the growth of the oscillations. And then we could talk about how the thread of the screw affects the moment of inertia and the placement of the two contact points. For data analysis, we could discuss how they could better predict the equations they set and compare that to the data.
Okay.
Okay. So first of all, in this discussion, we wanted to talk about the difference between a nail and a screw. As mentioned in the question, you said that you equated a nail to a screw because of the two different contact points. However, we wanted to talk about how the thread would make a difference in the moment of inertia of the screw, because the thread would both increase the radius, yet not increase the mass by a proportional amount as if you just had a bigger nail. Oh, sure.
So why do we choose to use the screw as a nail instead of a screw? Is because firstly it's easier to print. And we consider that it's done the same because when a screw is here, actually the thing on it is shorter, it's smaller than the radius of it. So it actually only affects the mass of the screw, but not but we didn't consider that.
However, wouldn't you consider that the screw actually contacts the thread of the point at certain types of screws, such as if you had a machine screw, there wouldn't be a thread together, and if you had a wood screw, normally the thread of the screw is much larger than the point, such that the thread contacts before the point, which would cause there to be an extra section over here, and then it would also cause the radius to be different from the point.
That's with you, but yes, if you said that this is not only point, it has a radius on it, it still has a smaller such a
Yeah.
if we consider this as a cone, we can also consider this as a cone.
Yes.
Do you agree?
Yeah, I do. Yes.
Yeah, so if this is only the point that tells us surface, we consider that this is the only point that tells us surface. But I totally agree with you that there might be a difference between the different materials that we think of now or we like the price now.
Okay, moving on, I wanted to talk about the pivot point. You did not really seem to say where the pivot point was. Could you showcase how you would figure that out? So when the screw oscillates, where does it rotate around the point?
You mean the point on the surface?
Yes.
So without the oscillation, it actually
Oh, with the oscillation.
with the oscillation, so the point here moves like this. So not only it oscillations,
Can you draw the length of the screw in relation to that point? So I could more clearly see which point you were tracking.
okay, so we drop the nail like this,
Yeah.
and so when the nail is oscillating, it drops the amplitude, and this point actually falls like also falls like this.
Could I restate the question?
Yeah,
I'm basically stating when you have a screw, right?
yeah.
And it's arcing in this motion. Would you say where is the pivot point? Would you say it's like on center mass, the tip of the screw, or someplace further out from the screw?
Also here.
You say here, okay. But you're talking about as if it's a cone, right? Are you when you say it's a cone, I'm assuming you meant a clock cone because there's like no point in the center, instead there's a radius, right? However, when a cone rolls, it rolls around the pivot point over here. So wouldn't you say that the pivot point should be further out, not directly here, in which case you need to track a distance further out?
So in our experiment, the actually is very thick.
Oh,
So we
okay.
just considered it as
So it's like the
so-
distance to the negligible that you could put it in the center.
Yeah, but I agree that if the radius is bigger, the
Okay.
yeah will be here.
Then I wanted to talk about how you could account for slip in the theory. Since you mentioned that you have a couple of different energy equations, you have energy is equal to the potential energy of the height, right?
Yes.
And then you add kinetic energy from the falling,
Yeah.
and then you have the kinetic energy from, I'm assuming you meant rolling of the screw, so like rolling along this axis,
Yeah.
and then also rolling along this axis, right? Okay, so you have kinetic energy rolling, and then I'm just gonna do okay, so what I wanted to ask was because in this form of rolling, we can see that the screw exhibits a slip on the motion. How would you factor that into the velocity calculation?
You mean the slipping down?
Yeah, so as it rolls, it kind of slips every so often.
Yeah. So the motion that moves downward is considered as the falling motion. The rolling is
Oh, okay, so
separated.
you considered that the rolling did not slip, and the moving downward was just kinetic energy translation.
Yes.
Okay, I also wanted to talk about the parameters. So you mentioned that you have new the friction coefficient constant to the experiment by using the friction bit. However, we think that the friction coefficient would have an effect on the amplitude of the swings. So if the friction coefficient was made larger, or there would be an increase in amplitude, do you agree that would be a factor?
Yes.
Okay. Then another parameter we wanted to talk about was the initial angle drop that you dropped the screw at. Where did you keep the initial? You mentioned you kept the initial angle constant. At what degree did you keep the constant at?
30.
So you dropped it at 30 degrees. Okay. Is there a reason why you only dropped it at 30 degrees? So like why 30 degrees in particular, and why didn't you dare?
We cut in 60 degrees also, but the amplitude is too big, then it oscillates for several times, and then it falls apart.
So if you wanted to consider a wider rise of amplitude, which would in turn affect the potential energy at the beginning of the equation,
Yes.
would you think that adding a longer board or perhaps a wider board would be helpful?
Yes, I think so.
Okay. We also want to talk about in the screw itself, the motion. We believe that there seems to be some damping because it's moving along the friction surface. However, you don't seem to mention that in your friction oscillations. Could you? So do you agree there should be some damping?
Yes, I agree.
Okay. Then if there is damping, what do you think is the factor that causes the damping?
I think it's the rotational friction that we can get
Okay.
on the tape.
Okay, what do you believe is the restoring force of the oscillation? You don't seem to mention it. Restoring force of the oscillation, why the screw goes back and forth?
Because when it gets to the specific height,
Yeah.
like the radius of the radius of the
Okay, also, we were concerned about the gap in the tape in the experiment, because the gap in the tape would result in an uneven surface and it would also affect the friction coefficient. Could you, we think that it would be better if you conducted the experiment with a single center of tape, or if you use a material that did not require the
Yes, I agree with you, but actually the gap here is that it's not flat. But actually the friction tip that we used is already not flat. But I agree with you that there is some.
Wait, so if the friction tip is not flat, how did you ensure that the friction coefficient was constant across? Or did you just not consider friction inside of the theory?
Yeah, we just want to increase the friction, but we can still see it as a flat surface if we want to observe the oscillation.
Okay, so it would be negligible. And then I also want to talk about your data analysis. I can see that you did not predict the amplitude using the equation. Could you explain how you would say your theory is correct then?
Because from the pendulum formula, you can see that the length, when the length is longer, the period will be longer. This is a prediction rate. It's my formula we've been mentioned before, but we can see that it is predictable because the length is the only variable that we are using right now. So
Also, you would predict the period in the back.
yeah.
Could you state how you would, since you didn't really mention it in the presentation, could you write out how you would model the moment of inertia for the arcing motion and the rolling motion?
So when the nail is falling,
Yeah, so you mentioned turning out by, did you mention this, what were the two items you came up with?
this is the inertia and this is the
Yeah, but like
rotation.
how did you calculate the inertia, moment of inertia?
Oh, we didn't do it. We just want to see that if one of them decreases, the other one. We just want to see the relationship between the different energies.
Okay. We thought that it would be a good idea to calculate the moment of inertia because, as you say, you also change the mass while you change the length, right? So because the inertia of the rotation would be equivalent to some factor of r squared, by changing the by calculating the inertia, you would be able to figure out more geometry by rewriting the observation. Okay. Also in terms of inertia, not just mass but the radius.
If we have the variable,
Not the radius, okay.
but when we are following it down, actually it kind of flipped over. And
Oh, okay.
yeah, so we didn't mention that, but
Okay, time's up. Opponent, summarize the discussion.
So in our discussion, we discussed the difference between the nail and the screw and how thread changes the inertia of the screw. And additionally, how the pivot point changes depending on the screw or nail. Because the opponent mentioned that the radius of the contact point of the nail, the friction was so small that the pivot point was assumed to be on the tail. We also talked about the energy equations from the reported slides. We agreed with their energy equations. However, we thought that they could define the terms clearer by using more formulas for the inertia and the angular velocity. We discussed how to factor in slip while rolling downwards. Then we discussed relevant parameters of the experiment that could be changed, such as the friction coefficient, the initial angle of dropping, and the length of the board. We discussed how the screw had a dampening effect on the oscillations and how that could be considered. We discussed the restoring force of the oscillation. We discussed what the significance of the gap between the friction tape and the
Okay, time's up. Question from the reviewers. Propose.
Thank you for the reporter and opponent. So I would like to start with the problem statement. So the problem statement mentioned that we have to use a screw. However, the reporter used a nail. So what's the differences between these two?
So as we stated in our discussion, the difference between a screw and a nail involves threading of the screw. Because the threading of the screw contacts the point at the point that is the tip at a
I
different
understand.
location.
So how about the reporter?
We consider the touching surface the same.
Okay, so how about the inertial momentum? Because it's a different shape. So do you think the inertial momentum will change?
I believe that the moment of inertia will change, but in terms of the model, you can model it similarly to
Okay, I got
the
it.
model.
So the next question is also the problem statement. It mentioned you have to learn the growth of the oscillation. So what is the main reason that the growth of the oscillation?
I believe the growth of the oscillation can be attributed to a variety of factors. However, the main reason is the difference in velocity between the two different head and contact points of the
Okay, I
screw.
got it. And how about the reporter?
I think it's also because there is a angle velocity, because we made an experiment of the higher.
Okay, now let's move on to the theory part. So the friction you guys are talking about is the static friction or kinetic friction.
I'm talking about the static friction coefficient since it's rolling.
Okay, how about the reporter?
I'm talking about the falling kinetic friction.
So you think it's kinetic one, and however the proponent think it's a static one. Okay, so could you please answer the what is the direction of the friction?
The direction of friction is the opposite in relation to the head of the screw's direction.
Okay, so how about the reporter, please?
For the top point, it's the moving downwards, so the friction is moving upward, and for the oscillations, it's against the
Okay, so due to we talk about the friction, do you think friction will be a constant?
I do not think the friction is constant in their experiment.
Okay, how do the
I think it is.
Okay, so do you consider a rolling of the screw a per rolling?
Do you mean like the direction of the rolling?
Yes.
I believe the screw rolls in relation to the friction force, so it rolls in this direction if it were going up.
Okay, and do you agree with the opponent?
Yes, I agree.
Okay, so let's move on to the experiment. So do you measure the friction coefficient?
No.
Okay, so do you think this is necessary to measure?
I believe this is necessary, but because they did not mention a dampening effect in the initial model, then they did not have to consider friction.
Okay, I got it. And while you change the length of the screw, so the mass will also be changed. So what will also be changed? The result. Which kind of result will be also?
The falling motion will also change.
Okay, so how do you think
I
about
believe I
this?
stated the mass of the screw will affect the moment of inertia.
Okay, and will the inertial velocity change?
Yes.
Okay, how about the point?
Yes.
Okay, thank you for.
Okay, so preparation time for review, 2 minutes.
It's fine, it's fine. I think you did. There's only one, I think they might not. I don't know. You can't bring that. You can't bring that. I mean, like, it will come before a suggestion. I suggest you use the predictive data using if you want to test if it's correct.
Reviewer, take floor.
Okay, thank you for the reporter and opponent. I'm the reviewer. This session I'm going to review question number 9, oscillating screw. So here's the problem statement. We may focus on the motion of the screw and the growth of this oscillation and the relevant parameters. And the test fulfill of the reporter is partly fulfilled. And here's a summary of the reporter's presentation. She meant focus on the growth of the oscillation and the motion of screw, and the series, the cone motion, and the simplify of the motion to the pendulum. And the setup and the analysis is the wooden ram and the sandpaper. And however, she used a nail, but the reviewer thinks that due to the problem statement, she should use a screw because the nail and the screw have different inertial momentum. And the parameters that she did is different size of the nail. And the conclusion that is to separate the motion of three parts, the folding part, the oscillation part, and also the rotate part. And here's the pros and cons of the reporter. The pros is that complete qualitative phenomenon explanation and lots of experiments to prove the assumption, and quantitative understanding of the problem, and use the energy to analyze the motion and identify different types of the motion. And for cons is that she's lack of quantitative comparison between the theory and the experiment, and lack of explanation of the experimental result, and analyzed method didn't be mentioned in her report, and the setup didn't match the problem statement. I think this is pretty important to use a screw. And here's the pros and cons of the opponent. The pros is that the modeling of the moment of inertia with the reporter and point out the problem of the energy terms. However, the cons is that they didn't understand the reporter's report and didn't understand the direction of the friction. So here's the discussion point of the opponent and the reporter. So the opponent asked about how do you calculate the friction coefficient? And the reporter answered that no, they didn't calculate the friction coefficient. And the reviewer thinks that since the friction is one of the important parameters in this problem, so the friction should be taken into the consideration and should be measured. And the next discussion point is that the opponent asked about the difference between different types of the screw. And the reporter answers that the thread will be smaller than the head of the screw, so it won't affect. However, the reviewer thinks that since the contact point of the screw can be in different position, and the nail can't be simplified as the screw. And I also mentioned that the inertial momentum of the screw and the nail will be different. And the next discussion point is that the opponent asked about how do you predict the amplitude of the motion, and the reporter answered that we can use the pendulum equation to assume it. And the reviewer thinks that the amplitude could be calculated. It's kind of the compound pendulum, so the equation might be fixed. So the next discussion point is that the opponent asks, do you calculate the moment of the inertia? And the reporter answers no. So the reviewer thinks the inertia of the moment should be calculated, and it might be two different inertia should be calculated since the rotation axis is not the same. And here's some midpoint the reviewer would like to mention. The first one is doesn't mention the difference between the nail and the screw. However, the reviewer has also already mentioned about it. And the problem statement mentioned to investigate the growth of the motion. However, I didn't see the investigation of the growth of the motion in the reporter's report, and suggest the reporter to measure the friction coefficient that the opponent also mentioned about the friction coefficient. And the next one is that the opponent has wrong understanding of the free body diagram that the reporter provides. So these are the next point the reviewer would like to show the juries again. And thank you for the reporter's report and opponents. Thank you.
Okay, finally, concluding a remark from a reporter.
Thanks for the reviewer, and I would like to make a conclusion. So first, I mentioned that the amplitude and the frequency is discussed in my presentation, and also we consider the motion as a falling motion, rotation motion, and also the oscillation. And the material of the nail is the same. So we control the length of the nail, the friction, and the slope, and we observe the position of the nail. And the conclusion is that for longer nails, we have longer periods and smaller vertical velocity. And for the future, we can decrease the angle of the seat to decrease the kinetic energy. And what I can improve is that I can talk more and calculate the inertia and also quantify my theories. And also, the differences between a nail and a screw should be considered because our nails is thin, so we can consider it as the same thing. But when the radius is bigger, we should consider them as different things. And also, the initial angle should be discussed. When the angle is too big, the nail will fall away. The friction tape as we have made an experiment before. And also the damping should be considered more, but like we have to calculate the friction and not only mention it. And also, we can use a single friction tape to avoid the gap between it. So we can make, and also we can make the stick wider and also longer to observe the more oscillations. And also the shape of a screw and nail can be seen as a cone. And the tracking point of a cone with or without a tip can be different. And also the mass actually affect the inertia and the falling motion, which we should consider more about. Thank you.
Okay, so question from a jury.
So I have a question to all three teams. So can you name all relevant variables in these, the parameter for the acceleration?
I think the parameters are the length of the nail, the radius of the head of the nail, and also the mass of the nail, and also the friction on the slope, and also the tightness of the slope is the parameters that will affect the nail.
Okay, and then opponent?
I believe the mass of the screw, the radius of the head, the radius of the tail, the radius of the arcing motion in the pendulum oscillation, the length of the screw itself, that kind of affects that, the friction coefficient, and the angle that's initial drop.
Okay, and the reviewer believes that the length of the screw and the ratio of the between the head of the screw and the body part, and also the inclined angle, and also the friction coefficient should be taken into consideration.
Okay, so any other questions? So one question here, same for three of them. Do you think the friction mainly affect the oscillation? So maybe from opponent.
I would like to clarify first that I misinterpreted the reporter's presentation, in that I was talking about the friction of the rolling that caused the rolling motion. However, the reporter was talking about the friction that affected the sliding of the screw down the ramp. Yes, I...
So rebound. Sure.
Wait, so I believe, yours is, this friction affects rolling motion, right? Or the oscillation? Yes, I believe friction affects the oscillation.
Okay.
Okay, the reviewer believes that the friction of the head of the screw and the body part of the screw will be different, so the friction will cause the oscillation of the screw.
Okay.
Yes, we believe that the friction on the head of the screw is bigger, so the oscillations will increase. The amplitude will increase while oscillating.
Any other questions?
Well, we all know that the rolling of the oscillation is a very important key word in there. So I wonder whether that energy comes from. We all know that the growing of oscillation should imply that the energy is coming from somewhere else. So what's your opinion?
We believe that the position energy is transferred into the
Rotation.
rotation energy.
Can you experimental data to prove it, either qualitatively or quantitatively?
In our experiment, when it's falling downward, the position energy is decreasing.
I know, but can you give the experimental data to quantitatively to prove that the decrease of the potential energy is more or less comparable to the increase of that rotational oscillation energy?
We didn't clarify it.
The reviewer believes that it's caused by two of the factors. And the first one is the gravitational potential energy, and the second one is the torque made caused by the friction.
The opponent believes that the reason for the growth in oscillations is due to the gravitational potential energy.
Thank you.
So any further questions from jury? So if not, so let's go.
This affects the entire oscillation.
So for reporter, 6, 5, 5, 6, 5. For opponent, 8, 7, 6, 7, 7. For reviewer, 7, 8, 7, 7, 8. Okay, let's take maybe short break 15 minutes.
它应该可以遵照我们给它的指令问句。有个人是大概你给他一起叫他去。
如果你跟他写程式，因为他资料都有确认过，但是
应该晚点。
output 也比较，比如说他有很多在做力扣的，力扣都是他都有看过啊，所以那个当然没什么问题。但是现在看，他没有去过这个，
推的是他一个备份简报是做能量的。
在做呢，要开始了。要开始。Okay, that's it. So now, yeah, let's start the third round. Opponent, yeah, please go to challenge the problem.
We would like to challenge problem number 3, siren.
Okay, you have 1 minute.
We accept the challenge.
Okay, so you have 5 minutes for the preparation and write down your name on the blackboard. Reporter, you can start your presentation.
Okay. So hello, judges and editors. I am JMC from No Riders, and I will be presenting slides. So the problem statement says, if you direct an airflow onto a rotating disc with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on the relevant parameters. So our main focus here would be what are the parameters that affect the sound produced by the disc, and how are the harmonics created and affected by the different parameters. So we will be going through our observation for the phenomenon and setup, our model with qualitative and quantitative theory, our experimentation, which is for the first harmonic testing, and for further experimentation on harmonics related parameters. So for observation, so the phenomenon is when the disk is spinning at a constant speed or non-constant speed, and you have an air jet or an air hose at a place on the holes, and there is air going through the holes, a sound can be heard, and a frequency can be heard, depending on how fast this disk is spinning. And so for our setup, this is our setup, and so if you look closer, here's our disk, and then we have a microphone on the top here to record the sound created, and we have a hose right underneath the holes that shoots air through the holes. So, and then we have a high-speed camera that we use for tracking, as well as water probe for the frequency collection. And we also use a power regulator that's connected to the motor to spin the disc. And we had tracking through FFT and tracking on that software. So other setup equipment, we use different types of discs with different types of hole sizes and even shapes. And we had an anemometer to measure the airflow, as well as a clamp to change the airflow speed. And so for our model, so sound is a longitudinal wave that propagates mediums through a mechanical vibration in a direction of the wave. And they are periodic compressions of air that goes back and forth. So in this experiment, and phenomenon. Air is going through the holes periodically as it is getting blocked by the disk. So the air is going through, and when the air is over the disk, it stops and while the air keeps going. And so you see this phenomenon that the air keeps moving, and then so there's a certain amount of pressure compressions of air per second. And so our theory is that the frequency you hear is omega times n, which is basically however many holes the air passes through per second. And so omega here stands for how rotations per second that the disk is spinning at, and the n is the amount of holes per rotation of the disk. And so this is our video. We had sound in this video, but since we couldn't play sound, we can't hear the sound here. So for our harmonic qualitative theory, an increase in airflow rate results in more turbulence that increases the amplitude of the higher harmonics. And so this may be due to the increase in turbulence with the increase of airflow rate. The increase of diameter of the holes also results in an increase of the amplitude of the higher harmonics. And so the turbulence is also increased with an increase of the diameter of the hole. And so as you will see later in the waves, there is a square-shaped wave, and this is seen in the pressure vs time graphs and this may be a result of turbulence. So the threshold for turbulence is given by Reynolds number. And so Reynolds number, turbulence occurs when Reynolds number is around 3,000 to 4,000. And so we have our equation here. Reynolds number is equal to the density of the medium times the velocity of the airflow times the diameter of the holes over the viscosity of the medium. And so since the density of the medium and the viscosity of the medium is constant, we set our equation is this, as we will be changing our diameter as well as our velocity of the airflow. And so we also look into vortex shedding. So vortices appear at all speeds of air, and vortices are basically when the air is going through the hole. Because of Bernoulli's principle, there will be vortices that are created, and this creates some of the sounds that you may hear in this experiment. And so vortex shedding appears at a Strouhal number of roughly 0.2, and so Strouhal number is given by the frequency of the sound you hear times the diameter of the holes over the velocity of the airflow. And so all the frequencies we collected are roughly above 500 hertz. So when we solve for B, the airflow speed has to be 25 meters per second for the vortices to appear, but then all of our experiments are done below 20 meters per second for the airflow speed, so we did not consider vortex shedding. So for our experimentation, this is an example of the frequency we collected. So as you can see here, the wave, the pressure versus time wave, you see that the shape is like square shape at the top, and then at the bottom, it's also square, but then because of turbulence, it creates a lot of different spikes. And so when the frequency, when the pressure is changed, the pressure can be changed into a frequency graph through FFT that the logger probe does for us. And you can see that this is the first harmonic, which has the largest amplitude and is the one that you hear the most. And you have multiple higher harmonics with less amplitude. And so for our frequency comparison, we tested our first theory. And so this is our data. And so we have a graph here. We plotted the experimental frequency as well as the theoretical frequency that we collected from our camera. And once we graphed it, we see that the slope is roughly 1, which means that the experimental frequency and the theoretical frequency is roughly 1 to 1 when the disk is spinning at the same speed and the airflow is constant. And so for further experimentation, the turbulence, so for turbulence, we experimented on turbulence with holes of diameter 0.01 meters and 0.02 meters. And so this is the equation. And so for when the diameter is 0.01 meters, we see that the prediction for the turbulence would be around 4.4. The prediction. So when the turbulence happens is between 4.56 to 6.08 meters per second for velocity when the diameter is 0.01 meter. And for a disc with a 0.02 meter diameter holes, the velocity needed for turbulence is roughly 2.28 to 3.04. And so when we compare the graphs, for the low velocity of air, we see that the graph is very sine wave shaped, which means that there is not a lot of turbulence, and we see that the harmonics all have small amplitude. And when we increase the velocity of the air, we see that a square shape is starting to form, and there are also more harmonics, as you can see. And when you increase it even more, you can clearly see that this is a square-shaped wave. And then when you increase it to an even higher extent, you start seeing disturbances in the wave, like these spikes. And as you can see, the harmonics, the higher harmonics are getting larger and larger with the increase of airflow. And so for 0.02 meter diameter holes, at a low airflow speed, you can already start to see a square shape in the wave. And then so you can also see that the amplitude of the higher harmonics is actually larger than the previous ones. And then when you increase it, you can already see at 2.5 meters per second, the wave is basically fully square shaped. And then at 3 meters per second, you see it's square shaped, and at 4 meters per second, it's also square shaped. And so we compare the air velocities or the airflow rate to the percentage overtone, where the percentage overtone is the amplitude of the higher harmonics added up over the first harmonic. And so we can see here, when with the 0.01 diameter one, the y is equal to, the slope is equal to 7.2, and whereas the diameter of the 0.02 one, the slope is equal to 13.04. So when you increase the diameter by 2, you can see that the slope is roughly increases by 2. So the 0.02 diameter one, the amplitudes of the higher harmonics increase twice as much as the 0.01 meter one. And we also tested with Reynolds number. So when we tested with Reynolds number, we plotted the graph, and I forgot to mention that after a certain frequency, it starts to stop increasing, which is due to the size of the holes. And so for the percent, we also compare the Reynolds number to the diameter of the holes, or the percentage overtone, and we see that the slope is constant because Reynolds number is a universal value. And yeah, and then so possible explanations for error is that there are a lot of ambient noises in a room that may cause these little spikes. And then so air hitting between the holes and causing it to, and then it may like spread out, and this may cause extra noises and disturbances. And air coming out of the hose also creates excess noises. And when the air is hitting the microphone, it actually creates a large noise that can be heard. And so a very important part is the microphone position with respect to the air jet in the hole. If the microphone is not directly on top of the holes, it can create a very different frequency. So we were very careful in experimenting to put the microphone right on top of the holes and the air jet. And so in conclusion, what causes sound created by the siren? So it is when the air is going through the disc periodically because of the pressure. And so quantitatively, the frequency is given by however many holes the air is going through per second. And so for the harmonics, what parameters affect the harmonics? So we discovered that the velocity of the airflow as well as the diameter of the disc affects the turbulence, and turbulence would increase the amplitude even higher of the higher harmonics and create a square shape as you see in the graph. And so this is when the Reynolds number is roughly 3,000 to 4,000. And so we also mentioned how vortex shedding is unlikely to cause the higher harmonics. Thank you.
Okay, I have a question from the opponent.
Okay, thanks for the reporter's report. I would like to ask, how did you analyze your audio film? By which type of film? MP3 or wave WAV?
Which
you analyze your audio film?
This was like MP3 because we use
MP3,
Logic
okay.
Pro.
Another question is, where did you place your microphone? In front of the disk or the back part of the disk?
Oh, like we had the microphone on the top and then the disc in the middle with the airflow on the bottom.
And page the power statement, please. Since the power statement mentioned that you have to investigate how the sound characteristic, do you think the amplitude of the sound is one of the importance about the sound characteristic?
Yes.
Okay, and did you measure the sound amplitude? Or
Sound
not
amplitude?
analyze?
Yeah, you could see the amplitude on the the FFT.
And okay, and did you place your holes on the disk evenly?
Yes.
Okay.
We reprinted it with, we laser cut it with this, yeah.
So the distance between every single
Each hole is the same, yes.
Okay, another question is, please turn the page that you show H equals to omega times n.
F?
The equations that you calculated the theoretical frequency.
This?
Yes. Is this your experimental result or the theory?
It's our theory.
It's your theory.
Yeah.
And where the theory come from?
Because frequency is just 1 over the second, 1 over second, right? It's just the frequency for which something happens, right?
So does the sound provided by the H tone? Do you think?
H tone?
Yes, H tone.
Okay, time's up. So preparation time still for opponent. 3 minutes. Opponent, you can take a floor.
Thank you for the reporter for the report. I'm honorable juries and fellow competitors. I'm the opponent, Ethan Xu from Typt for problem number 3, Cyrus. So as a purpose statement, it mentioned that the reporter should be talk about the explanations of this phenomenon and investigate about sound characteristics. And I believe that the reporter only mentioned the sound characteristic about the frequency, but not the amplitude. And about the summary of the reporter. First, in the theory, they mentioned about the harmonic qualitative theory, which they mentioned about the equation, but there is no any derivation about those equations, and they didn't calculate it. They can't calculate the amplitude of the equation or concluding the viscosity in their equations. And about the turbulence, they mentioned about the Reynolds number of the airflow will affect the result, but I can't see any of the things that I just mentioned. I can't see any turbulence or the viscosity parameters in the equation that to compare with the result. And about the voltage shedding, I believe that the voltage shedding is one of the important phenomena that makes the sound exist. But they didn't explain they didn't actually calculate the voltage shedding coefficient. And about experiment, the setup that they use the motor to rotating the disc, and they use an air source, and they control the air source, the speed of the air source, and they have the high-speed camera to calculate the omega, which is the rotating speed about the disc. And as a parameters, they choose the hole size, shape, and viscosity of the air. And about the method, they use fast Fourier transformation to find the frequency. But I would like, this is one of the points I would like to discuss. And about conclusion, as the amount of the holes rise, the frequencies will become higher, which can match to the theory that they provide. And the viscosity will also affect the sound, but I can't see any relationship between the theory about the viscosity. And here's the strength and the area for improvement for some suggestion with the reporting on the strength. The completely quantitative phenomenon explanation about the voltage shedding, about the harmonics, and they explain why the sound will exist because of the compression waves. And they have a lot of experiments to prove the assumption. Since they provide a lot of experimental results, but some error bars that has been discussed about. And here they are clear understanding of the report, and they have well explanation of the data. And about the area for improvement, they have lack of a quantitative comparison between the theory explanation that we just mentioned, that they change the viscosity, but in their theoretical model they didn't mention about the viscosity and the Reynolds number and they have lack of explanation for experimental results, since they didn't mention about the amplitude of the sound characteristic, that I believe that is one of the importance for a proper statement. And they have unclear physics picture and simple explanation of the phenomenon. And they have the unclear graph explanation, since that there are some error bars every equally in the same graph. And they have some equal error bar, but they have no error bar in some experimental results, so I would like to ask about. And they have lack of connection between the theory explanation, because some of the parameters they didn't mention in the theory. And they have made a sound absorb, they didn't make the sound absorb box for the noise absorbed. And they used an MP3 to do the audio film, but I believe that MP3 may cause the sound distortion. And about text volume, I will see that the reporter has partly volume for this test, since they didn't mention the full sound characteristic that they just mentioned about the frequency, but not amplitude. And I would like to start my discussion now. Could you turn the page back to provide the equation? The frequency. I believe that the frequencies were equal to omega times n. So you say this is your theory.
Yeah.
Is there any derivation about this equation?
Okay, so frequency, as we all know, is just however many times something happens per second, right? So this is, you can clearly tell that the frequency you are gonna hear is the one as however many times the air passes through the holes. And so because in our experiment we had a certain amount of holes per rotation, so we have to
So you provide the equation by yourself?
Yes.
So I would like to ask, since that you provide the equation by yourself, why don't you consider the viscosity which you just mentioned in our parameters?
We believe that we didn't change the viscosity. I feel like it wouldn't affect the actual frequency. It might affect the amplitude of the frequency, but not the actual frequency sound.
So do you think the Reynolds number is one of the parameters for the sound characteristic?
Yes.
So why don't you mention about the Reynolds number or the boundary of the
Because
Reynolds number?
Reynolds number describes the turbulence, and the turbulence is related to the different harmonics.
Okay, so you talk about the things that you talk about the harmonic, and okay, in my opinion, I think since that the reporter talks about a lot about the frequency, about the viscosity, and talk about the turbulence flow, talk about the Reynolds number, but the equation that they provided by themselves didn't mention those parameters. And then, since that you mentioned about the harmonics, could you explain it for harmonic to me? Harmonic.
You want me to explain what?
Yeah, the harmonics. That's you just.
Harmonics? Oh,
Yes.
we only, so what we did is, because we had Reynolds number, we used Reynolds number to describe the turbulence, which then we use to predict the harmonics.
Okay, so what's the definition about the harmonics?
Harmonics is just basically a multiple of the first harmonic because of the disk. The disk, when there are holes, everything has a certain harmonic created with it, right?
Okay, I think the reporters didn't explain well about harmonics, so I would like to talk about the harmonics. So the sound that we heard can be separated in different frequencies. And the harmonics is one of the sound characteristics that we heard in our ears. For example, for the first harmonics, which we can know as the fundamental frequencies, is that the measurements if we only measure the frequencies, we will find the fundamental frequencies. And so the harmonics in the presentation that they say, do you agree that the harmonic sound will be the manipulated relationship to the first harmonic?
Oh, the first harmonic, all the higher harmonics have to be multiples of the first harmonic.
Oh, okay,
Yes.
so could you explain why?
The harmonic is just because, well, harmonics are all just the multiple of the first one, isn't it?
So, in my opinion, I think since that the reason that the harmonic in the reporter's report can be the multiple relationship is because the holes on your disk is periodic.
Yes.
So if the holes on the disk is not periodic, the harmonic tones that we measure shouldn't be the
Right. So they're all spread out evenly. That's why we hear the frequency, and that's why the harmonics are almost.
Yes. So
yeah.
So that do you agree that the reasons that make the harmonic measure is multiple relationship?
Yes, it has to do with how they're evenly spaced out.
And then another question, please turn the page that you said your experimental setup.
Experimental setup?
I would like to ask where did you place your sound, your microphone?
So in this picture, because we were moving stuff, it's not directly above, but so we have our microphone directly above the disc.
Above the disc.
Yes.
But you say that compression wave is created in the backside of your disc.
What? No, I said the compression is because of the air going through the disc.
So if this is a disc,
yes.
you place them, and the airflow will place at this side.
Oh, do you want me to draw on the board?
Okay.
Okay, so let's say this is our disc, right? And then this is a hole. So we have our airflow here,
Yes.
and then the air is going through like this, and then so this is our microphone. And so there are periodic compression of air going through, and then when the disc turns, it stops, and so that's why there's a frequency.
So do you think there's any resonated that provides makes the reasons that you provide the sound?
Huh?
And
Can you
resonate?
Resolent?
Resonate.
Oh, resonate? Wait, so can you explain your question again?
Do you think the resonate is one of the reasons that the sound can be heard?
Resonate as in, yeah.
No. Things that you may, I would not say no. In my opinion, I think the reporters mentioned about the compression wave, and the compression waves have differences between the resonance. So I think the reason provided the sound will be the compression wave that the reporter mentioned. So I don't think the resonate is one of the reasons providing the sound, since there is no resonate, the area for the resonate in your experimental setup.
Obviously, the resonate can affect the disc because there's constant air going and hitting the disc, right?
So
but the actual frequency is determined by the compression of the air.
I'm talking about the resonate of the air. Do you think
Resonate, like
that the resonate of the air is one of the reasons that the sound could be heard?
it could be, yes.
No, since the compression wave is the reason that you provide the sound, and there's no resonate area for experiment, I don't think the resonance is one of the reasons that cause the sound. And could you explain the the concept of the fast forward transformation for me?
So I have a slide for this. So fast Fourier transform is just expressing a function in terms of complex exponential. So basically what happens in the program is they have a wave, and the wave, because it's a square shape, it's multiple waves added up together. And so what fast Fourier transform basically does in simple terms is it decomposes the wave into multiple frequencies.
So the simplified to explain about the fast forward transformation is that I just mentioned the sound that the human ears heard can be separated in different frequencies. And the fast forward transformation is to turn those frequencies separated that we can be observed, the harmonics and the fundamental frequencies that the sound provided. And could you turn the page that you showed is your experimental data? That's,
which one? For
okay, just this one. Why does the error bar is sound all equally in these cases?
Because all the errors are generally the same, because the errors come from the placement of the microphone. So yes.
Okay, please.
Because the error is coming mainly from the placement of the microphone, so we estimated the error to be roughly 20%.
Okay,
for all of them.
so since that the error you provided is the same, so will the result the same? You think?
Result of what?
Result of the experiment.
I mean, the result of what?
Yes, since you just mentioned that every single experiment has the same result, is that what you mean?
Wait, there are two different experiments.
Just every single parameter for this data point, do you think the result that you measure is every time?
Oh, so the error we put is the maximum error because it's impossible to find the actual error for this because
so why
of the
is
placement of the
error bar in every single data has equal, but has the same
right?
error bar?
So we put the maximum possible error on there because we don't know the actual. We can't actually figure out the error because every single trial because of human error, the microphone is placed slightly off.
So in my opinion, I think the reporter should wrong place about the error bar since that they mentioned about they mentioned about the errors that they provided, but the error bar in every single data point is the same, has the same length. So I think
we're just predicting the maximum error that can possibly.
So the error that you provided is predicted.
Yes, because we tested different errors. We tested multiple trials and we saw the errors that could happen.
Okay. So in my opinion, I don't think the error can be predictably that's assumed on the error bar. So another question that I would like to ask, you mentioned the critique of the overtone when direction that you can find the presence about the overtone.
Wait, so
have you talked about the overtone?
The overtone?
Yes.
So the different harmonics, right? The
Yes.
ones after the first one.
Yes.
Yes.
So did you mention, and how did you find the first overtone?
What about
First
the first
order
overtone? First order overtone, is it not shown in the FFT graph?
No, you have shown in your FFT since that the seconds of the seconds harmonic can be tuning as the first overtone.
Okay, opponent, please summarize the discussion.
Okay, and thanks for answering the question about the reporters. And the reporter mentioned that the reason that the sound provided is a compression wave, and they didn't create any area for the resonate, but they say that the resonate is one of the reasons that cause the sound to be heard. And they use the MP3 film to analyze the sound, but as we know, the MP3 sound to measure the sound as an MP3 will destroy some of the frequencies in the data. So I suggest the reporter can use WAV film to analyze the sound. And about the experimental result, they say they have the same the result that they provided is same, but they plot the error bar equally, and they say that the error bar that they provided is predicted. About the Reynolds number, they didn't mention about Reynolds number in the equation, but they say that it's one of the important parameters.
Okay, question from the reviewers.
For the reporter, we want to know that why did you choose to place the whole, like there are 3 rounds on the disk. If you didn't consider the radius of the disk as a parameter, why did you?
Because the frequency we're hearing is basically however many times the air is going through the hole. So if you put it closer together, then it's only going to affect the frequency, which is still measured from our theoretical equation.
Okay, so and we also observed that there are some holes that the distance between the holes are very small, right?
Yes.
Then how can you make sure that the air only goes into one hole if it is hitting the middle distance of the hole if the distance is smaller than the air?
So it's hitting. Wait, can you explain it again?
Because like these two are the holes and this is the distance between it.
Right.
If the area you are given has a bigger radius of the holes, how can you make sure that it is going through only one hole?
Oh, we actually did our experiments with holes that don't overlap, so the space between them are actually larger than the hole.
And also we want to ask the opponent that what do you think for the parameters, which one the error will be greater?
I think the error that they provide the different viscosity will be greater, since that the viscosity is hard to control.
What do you think will change if the viscosity of the disk rotation?
I think that the viscosity can relate to the vortex strain that provide the sound. So if the viscosity is larger, according to the equation that provides the sound should be, the amplitude of the sound should be larger.
Thank you.
Okay, so 4 minutes for the preparation time of the reviewer. Okay, so the viewer will take the floor.
So I'm the reviewer from Team Waku Waku, and I'm going to talk about the problem siren. So this is the problem statement, and the task that we think they should do is construct a reliable experimental setup with a reproducible results, and also qualitatively and quantitatively explain this phenomenon, and also investigate the effects of the important parameters and experimentally verify that how they affect the phenomenon. So to summarize the reporter's presentation, the theoretical analysis that the parameters that they choose is the hole sizes and also the shapes of the holes. And they considered sound as a longitude wave to explain their theory, and also and they observed the turbulence. And for the experiment, they're testing the accuracy on the formula that they said the frequency is the omega times the numbers of the holes. So these are the pros and cons for the reporter. We think that for the theory, he had a detailed explanation and also good theoretical considerations. And for the experiment, they varied many parameters. And also, they have sufficient experimental data and theoretical verification. And the theoretical and the experimental analysis highly matches in their experiments. And also, for the structure, they have good diagrams and animations, and also they have explained the arrows in some points. But in the cons that we think is they can quantify the specific frequency more in their presentation, and they can consider the noise in the static state to decrease the outer disturbance of the deviation. And also lack of introducing the geometry of the holes because they mentioned about the shape of the holes. And also can compare about the pressure before and after passing through the holes then to quantify. And these are the pros and cons for the opponent. The pros are they have clear thoughts and questions for the reporter and also extended discussions on the parameters that they have mentioned. And they considered many details that maybe the reporter didn't consider so much. And also they have a well summarized of the reporter's report and also mention the relationship between the theory and the experimental data should be quantified more. And the cons is that mainly focus on the experimental setup maybe can extend more. So for the short question, the opponent asked that what is the audio measured, and the reporter said that is by MP3. And also asked about the microphone placement, and reporter's response is that directly above the disc. And the reviewer partially agree with the reporter, but we think that they can also try to decrease the outer disturbance by measuring the initial sound in the static state and try to decrease it. And also, the point raised by the opponent is that consider the viscosity of the holes, and the reporter's response is that it doesn't affect the frequency so much. And we partially agree with the reporter, but we think that the viscosity can also be considered as a variable if there are any future experiments that we want to check. And the opponent asked that is there a resonate, and the reporter's response is yes, and we think that the compression wave that the reporter said is a factor which there is not a resonate. And also the opponent said that the error bar is the same length. So and the reporter response is that the error bar is actually.
Time's up. So reporter can please give a concluding remark.
So the opponent asked about how we define or derive the equation for frequency, and we just derived it because it's the frequency is however many times something happens per second. So basically it's just however many times the air is going through the holes per second. And so we use Reynolds number to determine turbulence. Okay, and then we had higher harmonics. Oh, we did say that the higher harmonics should be multiple of the first harmonics due to the spacing of the holes, which are all equal. And then so the frequency should be based on the compression of the air, not the resonance. And I think we were unclear with that with the opponent. And so the error bars that I put on my graphs are actually the maximum error that we tested because it is impossible. Every time you do the error, it is different. So we tried to put the maximum amount of error we can on the graphs to show how much you can change. And so the opponent talked about how the MP3 player would affect the sound because some of the sound may not be picked up by the MP3, but that doesn't affect our data much because we can, as we see in my graphs, all of the frequencies we care about are there, and then we see all the first harmonic and how big it is, as well as the higher harmonics. And so changing the viscosity may actually change the turbulence, but it will not change the frequency of the sound because viscosity does not affect the, because the sound is only affected by however many holes, times the air is going through the holes. And although we do not have the data for the different shaped holes that the reviewer talked about, we did actually did experiments on it, and we didn't find anything too out of the ordinary, so or a difference from a circular hole.
Okay, thanks. The question from Julie is,
I have a question for the reporter. I remember the opponent claimed that your group didn't do any amplitude analysis. Do you agree with that?
Yes.
Okay.
You
didn't
yeah,
do that?
we didn't think that, we didn't analyze the amplitude, but we did have a lot of amplitude stuff on the FFT. So,
But you didn't talk about it.
oh, because when we tested with even, so we had, when we recorded, it recorded once every 10,000 times per second. So when we turned it up to 30,000 times per second, the amplitude increased, which showed that, yeah, so we didn't think it was important for us to discuss too much about the amplitude.
Thank you.
okay, so I would like to ask one question first about the opponent. So if I increase the rotating speed of the disk, do you think what will happen?
I think the fundamental frequency, which is the frequencies, will be higher, since according to the result of the reporters and the equation that they provide.
Okay, so the other question for reviewer. So the same, the rotating is speed is higher. Do you, can you observe the multiple harmonic? Yeah, yes or no?
Yes. Yes.
Okay. Okay, any question?
Okay, so the reporter gave an empirical formula for the sound frequency. So I would like to ask three teams that to give a simple physical explanation for the derivation of this equation. So let's start with the reviewer. Can you give a simple explanation how that equation gives you the right sound frequency?
So the numbers of the pressure of the air affects the velocity and the when the disk is rotating, it's actually like the hole is closing, opening and closing when the air is coming through. So the numbers of the holes will affect the amount of times and the frequency of the time that the hole is opening and closing. So it will affect the frequency.
Okay, then let's go to the point.
So, but in my opinion, I think the phenomenon that makes a sound change is that the air should be caught by the disk. And so, since that it will depend on the cut of the disk, so the rotation speed can be related to the frequency. Another effect is that the holes of the disk will also change the frequency that they cut the air. So I think that according to these two reasons, we can write a simply experimental frequency to count the frequency that in the equations.
Okay, so the airflow is alternately cut off by the disk. So basically what happens is the air is going through the disk at regular intervals of pressure. Like there are regular intervals of pressure that's going through, which creates the sound that we hear. And that's why our equation is for frequency.
Okay, so any further question from jury?
Okay, so we all know that different instruments, they have their own characteristics, right? So here, what would be the most important? Frequency. So you have frequency, amplitude, and something else. So what do you think is the most important to describe or distinguish different instruments?
Since The reason that I think the characteristic can be depends on the amplitude and the sound frequencies is that these two factors can depend on the wave shape about like the human ears heard.
So we think that the unevenly placed hole creates different wave shape, which we agreed at the opponent that we can hear three different wave shape of the sound.
We believe that the frequency is most important because different instruments have different sounds, but what we hear are different tones or pitches of the sound, and so those are frequencies. So yeah, those are the most important because those are the ones that distinct the distinctness of the sound. Yeah.
Okay, so score is fine. Okay, so for reporter, 7, 6, 6, 6, 6. For opponent, 6, 8, 7, 6, 8. For reviewer, 5, 6, 6, 6, 6. Okay. So finally, I would like to ask the jury, do you have any suggestion or comment for all participants? Okay. So if not, so I would like to close this section. So I hope everyone can enjoy the rest of the day in our campus. Okay, thank you very much.